ready, Barry?
Yes, Rob.
3, 2, 1, fire. This is a linear induction motor. It uses about 100 kilowatts, and it can accelerate 4-pound missiles such as this up to nearly 100 miles an hour. Ready again, Barry?
Yes, Rob.
Fire. This is a big motor. On the other hand, in this thimble, I have the rotors of over 10,000 electric motors. And nobody is going to deny that these are small motors. Now, a linear induction motor like this is an easy thing to understand because it's just like a flowing river. This is a river bed. If I dip a piece of wood into the river, turn on the water, the first thing that happens is that the wood floats. It rises up, and then when the river is flowing nicely over the weir, I let go the wood, and it soon attains the same speed as the water. If, on the other hand, I dip into the river a cylinder like this, which is free to spin, then the river spins it, and notice which way it spins. The water passing underneath it causes it, as it were, to roll backwards. Now let's look at this linear motor, which is just like a bit of the big machine we've just been seeing. And this is like a river too. In this case, I'm going to put in a magnetic piece of wood, which is a piece of aluminium. I turn on the current, which is like turning on the water, and the magnetic wood floats. When I let it go, it soon attains the speed of the river. But of course, in this case, the speed of the river is much greater than was the speed of the water. Again, if I dip a cylinder, this time a copper cylinder, into the magnetic river, it spins in the appropriate direction. We can have a shallow river. There is a shallow river. Or turn on some more water, and there is a deep river. And when I'm making these comparisons, I'm doing what every engineer does almost every day of his life. I'm using an analogy. Now, a good engineer knows when to use an analogy and where it breaks down. And I'm going to show you where this one breaks down. If I take a heavy cylinder, such as this, and place it in the river, and then turn on the water, you see the flow rolls the cylinder downstream. If I now place the same cylinder in the magnetic river and turn on the magnetic water, it rolls upstream because you see the river is flowing that way. It doesn't matter whether I use a small cylinder or a long cylinder, and these are all of copper, or whether I use a steel cylinder, they all roll backwards. A steel ball rolls the same way. So does a steel washer. Of course, you can have a lot of fun with this. This all-plastic motor car has had 4 steel wheels fitted. There's the engine, and when you release it, it goes quite nicely. Now, why is this? Why do all these pieces of metal roll backwards along the field? To understand what's going on, we need to look at the shape of the field lines over this motor. They come from a north pole into a south, like that, and the whole field pattern is moving along, like the magnetic river. Now, suppose we could sit at one place over the machine, such as in that little square, and watch the field lines go by. Notice the direction of the arrows. At the moment, the field is to the left. Now it's upwards, to the right, downwards, left, up, right, down. So it's left, up, right, down. And the rotation, you see, is clockwise, which is to say, rolling backwards. So the whole machine behaves like a mechanical rack and pinion, in which this is the field and this is the rotor. And here is the action. Well, of course, mechanical things are easy to understand. But when we make it magnetic, it's a little less obvious. But we put in a row of horseshoe magnets, and the action, as you see, is very similar indeed. This, then, we call a rack and pinion motor. Now, in a linear motor, a row of electromagnets effectively replaces the row of permanent magnets, and instead of the many-toothed wheel, I'm going to use a very simple wheel with just 2 teeth. When I switch on the motor, the wheel spins, and if I disconnect one of the wires to this motor, I can stop this travelling field dead, like that, and now we can see the shape of it. There is the field shape. If I draw the wheel slowly along the surface, you can see the rack and pinion action in slow motion in the stationary field. Now if I reconnect, I shall start the field moving again and spin the wheel. Now the rotary version of this machine is what drives an ordinary electric clock. It has a toothed wheel which moves inside a set of teeth on the stationary part. When I switch it on, there is a clock motor. Motors with steel rotors are purely magnetic machines because they don't depend for their action on any electric current flowing in the moving part. Unlike, for example, this copper cylinder. Now when that spins, it does so because an electric current is caused to flow in the copper. And so I call this an electromagnetic machine. Now by far the most intriguing magnetic machine for me can be made simply with an ordinary paper clip. First, I unroll it, and then wrap it around a pencil or other non-conducting rod, and then offer it to the linear motor. Now, this spins very well, as you see, and yet there is clearly no electric circuit, so no current can flow in the clip. Now I want to distinguish very clearly between magnetic machines and electromagnetic machines. Both types are used extensively, both in industry and in the home. A washing machine, for example, uses an induction motor, which is an electromagnetic machine. Electric clocks, as we've just seen, are magnetic machines. Now, magnetic machines get better as they are made smaller, whereas electromagnetic machines are better as they are made bigger. This last fact I can prove to you in more general terms by using what I call my goodness models. Now, every machine has a magnetic circuit which I represent like this. The flux in that circuit is made to induce a current into an electric circuit which links it, like that. The force you can get from a machine is proportional only to the product of the flux in the magnetic circuit and the current in the electric circuit. So flux and current are the things you want lots of. The thing which stops you having as much as you'd like, of course, is the resistance in the case of the electric circuit and the magnetic resistance, or reluctance as we call it, in the magnetic circuit. The resistance of an electric circuit is proportional to its length and inversely proportional to its area. So if I take a second electric circuit, which is twice as big in every linear dimension as the first, then its length will be twice as great, but its area is 4 times as great. So the resistance of the big circuit altogether is only half the resistance of the small circuit. And when we put the 2 circuits together to make our machine, the combined effect of the 2 is to make the big machine 4 times as good as the small one. So it seems as if the rule for electromagnetic machines is that the bigger they are, the better they are. Now, with purely magnetic motors, the rules seem to work the other way around. Let me show you what I mean. These sheets are made of rubber, but it's rubber which has been impregnated with a magnetic material, and they've been magnetized so that the whole of that surface is a north pole and the whole of that is a south. And yet, there doesn't seem to be any measurable force between them. They behave as if they were unmagnetized. But if I take some scissors and cut two pieces from one of the sheets, then we see how those behave. There's no noticeable repulsion, but at least there's some attraction. And if I cut smaller pieces still, then at once there's attraction, and this time there's even some repulsion. Put one piece on top of the other with reverse polarity, and it just doesn't want to know the other one. So magnetic things get better the smaller they are. Now let's apply this principle of size to our fascinating racking pinion motors. I'm going to put a plastic tray on top of my row of coils, and I'm going to roll along its surface some split steel washers. A smaller one should go better still. Very lively. Now this experiment poses the intriguing question, just how small things can I roll? Can I literally spin an individual iron filing? Well, the answer is that I can. And to demonstrate this, I'm going to cover the entire surface of the motor with iron filings. And switch on, and you'll see what happens. Well, I don't know what you expected to happen. I know the first time I tried this, I certainly didn't get the result I expected. Look at the way the walls are forming. Walls of filings, spacing themselves from each other. The spacing between the walls depends on their height. So I can comb this lot like I could comb my hair. All I'm doing now is flattening the filings down, and as I do so, they get closer together. If you look at an individual wall, you'll see that the bulk of the filings in it are actually at rest. It's only the ones around the outside which are moving, and they're producing a gradual drift backwards along the field. Many of the experiments we've been doing with iron filings can be done with much simpler apparatus. For example, all you need is a horseshoe magnet and a means for rotating it. A plastic dish can be clipped over the magnet, and then into the dish we put a steel ball. When I rotate the magnet slowly, the steel ball just goes round opposite one of the poles. That isn't very exciting, nor is the fact that when I turn more quickly, centrifugal force flings out the ball to the sides of the dish. But if I rotate more quickly still, the steel ball will become a rack and pinion motor. There it goes, rotating backwards in the travelling field. Let's put some iron filings in the dish. Turn the handle and see what happens. At once we see the walls building up, and the backward rotation, and something else. Can you see the spirals of filings running up the hill into the middle? The inward movement of these filings implies there must be an outward travelling magnetic field to produce it. And if this is true, then it's very exciting indeed, because centrifugal magnetism, which is what this would be, is unknown at present. But if we turn the handle more slowly, and watch what happens in slow motion, we can see that the filings form into lozenge-shaped solids, and these are rolling over and over and spiralling into the middle, for the same reason that any rolling object traces out a spiral on a flat surface. So we hadn't made a discovery at all. But of all the phenomena we observed with the iron filings, the most striking perhaps is the building up of the walls. It tells us, among other things, that when we make a rack and pinion motor, we shouldn't use a solid cylinder like this. We should divide the cylinder into a number of discs. These 6 steel discs have been spaced to match the spacing of the walls in the iron filing experiment. They are going to wind up this cord, and in doing so lift a 2-kilogram mass. The discs will spin at 3,000 revolutions a minute. That is a lot of power to extract from such a small amount of material. In fact, that rack and pinion motor produces more power for its size than any other type of hysteresis motor. The shape of those discs is very similar to the shape of a coiled spring. At least it is magnetically. The most recent research that I've been doing has been concerned with rack and pinion motors of this kind, where we put a very small spring inside a glass tube, because this could operate as a self-contained pump, a helical pump. This spins very nicely. And of course, smaller ones, being magnetic machines, operate better still. And I can spin this spring about 3 inches above the surface. Now, if I can develop these to the stage where they will be small enough to operate inside living tissue, then they could be very useful to the surgeon during operations. If this should be successful, then I'm never going to forget that it began with no more than a paperclip and a pencil. This, then, is the world of small motors. Now, I don't have to tell you that this is a big motor. In fact, in terms of diameter, it's one of the biggest made. Its rotor is this aluminium disc. So it's an induction motor, and therefore an electromagnetic machine. And in spite of the fact that the moving part is rotary, it is a test rig for linear machines. Let's have a look at the driving unit. This row of coils is a linear motor which has been bent slightly to fit the shape of the disc. The speed of the field on this motor is nearly 300 miles an hour. And motors of this kind are being developed to drive very high-speed passenger-carrying vehicles of the future. Now, to test such machines on an actual track would cost a very large sum of money. You'd have to build a track many miles long to get up to this kind of speed. But on this disc, we shall be able to get real speeds at the edge of the disc of nearly 300 miles an hour. So let's switch it on. Power on. But remember, whether it's a big, complicated piece of machinery like this, or if it's simply a paperclip and a pencil, in the world of motors big and small, the work you've just seen is only the beginning.